And first of all, thank you for the kind introduction. Am I audible?
Yes.
Great. So, yeah, it's good to be back in GDG Coimbatore. Last time when I was here in 2019, things were simple. Like we had a very simple life pre-COVID. It was an era of word-based models, and now fast forward to 2023. Like everything has become big. Even GDG Coimbatore has been scaled to a bigger extent, and same with the LLMs that we see now. So scaling comes with its own challenges. So the intent of this talk is to speak about the challenges that we have in LLMs, large language models, and so we'll first try to understand what are the challenges that are there with large language models, and probably we'll also discuss about some of the techniques in overcoming those challenges. So in this talk, so it will mostly be like understanding about LLMs, and then we'll be seeing like a few, like 4 to 5 techniques wherein we can overcome the challenges that we have with large language models. And it will be specific to how we can adapt the open source language models, the llamas of the world, the Mistral, and so on. So I think we can get started. Yeah. So I'm Logesh Kumar Umapathi. So I'm a lead machine learning research engineer at SAMA. So I lead a machine learning implementation for a product in SAMA. And apart from that, I do contribute to open source. So I was one of the contributors of StarCoder, the StarCoder model that is built for code generation. And yeah, to get started. So yeah, before solving any problem, it's always good to understand what the problem is. So I will start with understanding the problem. So this is how a typical autoregressive based large language model works, like our GPTs of the world. So here I've taken this visualization from the wonderful blog from J. Alama. So here you can see that when we generate a sentence from a large language model, so here for example we have given an input as recite the first law, and each words are generated one by one. So first A is generated, and based on A along with the other inputs that we gave to the model goes as an input to the next step, and then the next token is generated, and so on and so forth, right? So in the era of BERT-based encoder-based models, we were mostly safe if we are able to parallelize things. We can fit as many sentences in a batch, and if we can feed that into BERT, we are good because the parallelization would take care of it. But the challenge with autoregressive nature of the large language models is it is sequential in nature, right? So you have to generate the first token, second token, third token. We can't do that parallelly. So that is one of the challenges. And it also brings to another challenge. That is when a first token is generated, so there is I don't know how far everyone is aware of what is self-attention is, but so in a typical self-attention mechanism, whenever a word is given us or a token is given as an input, that is typically a query vector. That's what you see in X there. That gets multiplied with the weights of query key and value matrices that we have, weight matrices that we have, and that generates QKV. So as and when we generate a token one by one, this key and value matrices, weights, needs to be maintained in our model. Either we have to maintain in our model, or we have to like recompute it one by one. For example, so there will be a KV vector that will be generated for a token A, and similarly there will be a KV vector that will be generated for robot, and so on, right? And the thing is, you need the previous KV vectors for you to calculate the next token's KV vector as well. So either every time when you predict a next token, you can repeat the calculation, compute it one by one, repeat it, or you can save that in a memory. And let's say once you have calculated it for A, you can save that in memory, and then you can use that for robot. And once the robot is calculated, you can also append it to what you had in A and save it, and so on, right? But when you do that, so here, this is a trade-off between compute and memory usage, right? Either you have to do more compute, or either you have to offload that to a memory when you are saving the KV vector. So this mechanism of saving the KV vectors is called as KV caching. And this is one of the challenges with large language models. So when you are building large language, when you are generating a long sentence with large language models, it can easily, the KV cache become very huge, and that would become a limitation for you to either generate a long sentence or fit in a large batch into your inputs. So, sorry, can you full screen? Yeah. So let's try to understand the numbers behind this problem. So typically, like if you have a billion or a multi-billion parameter models, the amount of memory that you would require to just to load that model into memory so that you can inference is the one. Like it all depends on the floating points that you have, the precision that you have in your model. Like if it's int8 based precision, then it's 1 bytes per parameter. So if it's 7 billion, you would require like 7 GB of VRAM of GPU. And if it's like FP16, it is like 2 bytes. So if it's 7 billion model, we would require a 14 GB or so of memory. And if it's FP32, again it's 4 bytes. So we would require like 28 GB or so just to load for the inference part. And so this is the earlier slide talked about just to load it into memory, right? But if you want to like generate a sentence or a set of tokens, what would be the overall memory cost of it? So this is the formula to calculate KV cache that is required, the KV cache that I talked about previously. So 2 as in there is like equal K and V vectors, right? So that's why we have 2 first. And we are assuming that the vectors that we are going to save are FP16. That's why the second 2 comes in here. So we have the in self-attention and implemented in a transformer or a large language models. Usually they are repeated across number of layers that we have in the transformer architecture, and it also repeated across a single layer which is called as heads. So that's why n layers into heads, and then the dimension of head. So this is what you need to calculate when a model predicts one single token. The memory required for it is this 2 into 2 into n layers, n heads and d head. So that was our formula, right? Let's see an example here. So here, for example, a star-coded model, which is a 15 billion model. If you want to inference it, the amount of memory that you would require, since it's FP16 based, 2 into 15, 30 GB of VRAM you would require for in your GPU to be loaded. And then to calculate the KV cache, right? So using our formula that we saw before, 2 into 2 is 4, and then this star-coded model has like 40 layers and has a 48 heads, and the dimension of each head is 128. So it takes roughly about 0.0098 GB of memory to generate one token, if it's a multi-head attention. So there are different variations of attention, like how you share, like it's shown in the diagram below. If you have value and key vectors for every query that you have, that is called as multi-head. Or if you group, and like let's say if you have minimal number of k and v vectors for every query that you have, that's called group query. And then if you are reusing your k and v across all your heads, it's called as multi-query. So if it's a MHA multi-head attention, 0.0098 GB is what you require. If it's a multi-query attention, since you are reusing the query and v vector, we can eliminate the one parameter from our formula, that is n heads, since it is repeated and reused. So it will just be 4 into 48 128, it's 0.002 GB. So it might look very small, right? But if you do the calculation, let's say if I'm using a 840 GB of 40 GB GPU, 30 GB would go into fitting my model into memory. And then to calculate the number of tokens that I can generate, if you divide it by the 0.0098 of MHA, right, I can only generate 4,000 tokens. So that would be like batch size of 4 for 1024 or so sentence, right? Which is very less for a production system. And if it's MQA, you get the advantage of using MQA. It is much faster and lower in terms of memory usage, and you can also generate a much longer sentences, or you can fit much bigger model into bigger sentences into your model. So probably a thumb rule is MQA in terms of memory and speed is better than GQA is better than MHA, but there is a trade-off between MQA and GQA and MHA in terms of accuracy. Since there are more reuse happening in MQA is comparatively shown to be like less accurate. But if you are deciding on using a model for your inference, probably you can take this thumb rule. We don't have to always do this math ourselves, right? There is a Hugging Face space. Someone has built this for it. You can use this space for calculating how much memory it would require for you to train or inference a model. Okay, so summary of the challenges, right? At least from whatever that we saw here. First, auto-regressive nature of decoding. So since with LLMs we have to generate token by token, we can't easily batch the sentences that we have, similar to what we can do with BERT or even prior models, right? That is one challenge. Second challenge is memory bound nature of it. Since the KV cache is built as we generate tokens, and it also explodes as we build tokens, the whole generation is mostly memory bound. If we are like doing it for small batches, and it's not compute bound. And it's also the memory consumption is increasing as we generate more tokens. Third is the ineffective batching, which also like similar to what we talked in the first point. We can't batch it effectively because every sentences will have its own tokens to be generated, and it will have a different sequence length. We'll see that in detail in the coming slides. So yeah, these are the challenges that we saw. Let's see how we can handle this. So there was one technique or a method that was introduced in this paper: flash attention, cost and memory efficient exact attention. So here, since our generation is mostly, the text generation is mostly memory bound. Before that, to understand this, we need to understand the high level architecture of a GPU, right? So we have main memory, the CPU DRAM, which is like we have a bigger amount of bandwidth there, 1 TB or more. And then we have the GPU, HBM or VRAM as we call it. So for A100 typically it is 40 GB, but the transfer rate in memory is like just 1.5 TB per second, right? But when it comes to GPU SRAM, it is very small in nature. That is, it is like 20 MB of size, but the memory transfer rate is much larger, like 19 TB per second. So this flash attention uses this to its advantage. So whatever the calculation, whatever the memory transfer that is done, this flash attention mechanism pushes that mechanism into SRAM. So they divide the big KV cache into small tiled vectors, and then they push that into SRAM. They do all the calculation in SRAM. So there are like, to calculate self-attention, there are like different calculation that you have to do, right? Like it's shown in the right side. We have to do mat multiplication, and then masking of the attention token, and then the softmax, dropout, and mat mul again. So when you do all this, when you do it in let's say HBM memory, you as and when you complete one task, you have to transfer the output of it to the next task, and then that has to continue from so on, right? So there is a cost involved in transferring this weights. So what the authors have done is they have used something called as fuse kernels. So instead of doing all these calculations separately, they do it as one chunk. That one chunk would take care of all the calculation. So they split that split the KV cache into small tiles. They execute that in the fuse kernel so that the memory transfer is reduced a lot. And then finally they combine all the calculations that they did to get the final KV cache and the documentation. So this is the overall view of flash attention. So this way, right? This is currently it's mostly a de facto way to train a LLM or inference an LLM. It has become a de facto way because of its advantage. Like we can fit in lot more sentences into the model with a lot less memory that we need. So if you want to use it along with transformers did a recent integration to flash attention. Like if you want to integrate that, you can use this snippet. You just have to add from pre-trained usual API. Just need to add use flash attention 2 equal to 2. And before that, you might have to need to like check whether your model supports flash attention. So there is probably if you go into the transformers repo, and if you see the implementation of your code, implementation of the model code, you will always have a separate class called flash mistral, flash llama, and so on. That is there when flash attention is supported. You can very well enable it and get the efficiency out of the box. And if you so prior to this was recently done. Prior to this, and there is also a version of flash attention which is called flash attention 1. That is what I explained in the initial slide. There was also an improvement further made over flash attention V1, that is V2. So if you want to use V1 for some reason, let's say you are stuck to a certain transformers library, and if you want to use a V1, this is probably the way to do it. You can install better transformers, and from better transformers you can enable flash attention to do it. And so there is this wonderful library or tool called text generation inference from Hugging Face. I don't know how many have heard about it. So this is like currently a workhorse for anyone who wants to like implement LLMs and expose that as an API. So if you are using, and this is also very easy to start with. All you need to do is run a Docker container and then pass a model to it. It will take, it has most of the optimization and goodies baked into it, so it will take care of most of the things, including the flash attention. So like if you want to enable flash attention in text generation inference, you can use this method. So it's already comes part of the library. And you can check whether your model supports flash attention in the text generation inference model. You can see whether your model has a flash prefix to it. If so, it will definitely support it. And so whatever we saw before, especially flash attention, so it would work well for a longer batch size because The nature of it is that we are tailing at a batch level, and then we are offloading the calculation to a fuse kernel. But when it comes to inferencing, and especially from when you want to inference like a long sentences, what would happen is you may not be able to use a higher batch size, because obviously like a longer sentence would take in more memory, so you can't use a bigger batch size. So in that case, the effect of flash attention is relatively less. The speed up that you get from flash attention is relatively less. So that's when the authors of flash attention has come up with a technique called flash decoding, where this is specific to long sentences. When you enable flash decoding, the KV cache is so initially when you don't enable it, so the KV cache has to be calculated, the tailing has to be done at a one sequence chunk to another sequence level. But when you enable flash decoding, it is done at a parallel. At a sequence level, it is done at it is parallelized at a sequence level, and then everything is reduced and the final calculation is calculated. So this is very new method. You can check Xformers library, so they have implemented it. If you want to use, they have a wonderful example of how to use that with Llama. You can very well try that. So in our benchmarks when we internally did, so the flash decoding was able to give us like somewhere around 20 to even 70% improvement when we are generating long sentences. And so the second challenge that we saw in the summary slide is batching. So the challenge is that when you have like 4 sentences that is coming into a model, right? One request could be for let's say a chat-based request. Someone is saying just hi, right? And the model just have to respond with hi. The other S2 could be something like someone has asked to summarize a document. So the S2 could be of longer sentence, and S3 could be someone would have asked to like do some kind of classification, right? So this is how typically LLM, when you have deployed like a model, LLM as it's good in general problem solving, that is, it can attack any problems. So usually a typical scenario will have one LLM and you'll be using it for multiple use cases, right? So, but when you fit in like the 4 sentences into a batch, each sentences would end in a different sequence length. Like just when a request for hi comes up, then the model responds with just an hi or how are you, right? It's just 3 tokens and then it has to end. But the second sentence, which is about summarizing an article, right? It may not complete in 3 tokens, it might take a lot longer to complete. So this way, when you do the batching, you can't, but you have to wait till all the tokens are, all the sentences are completed the generation, and then you have to fit in a new batch, right? So this essentially is not effective. So this is called a static batching. So that's when folks at VLLM, there is a library called VLLM. If you have heard about Vicuna and other models, they are LLM syschat. They are part of that team. So they come up with an interesting method called continuous batching. So wherein instead of waiting, this is very intuitive, instead of waiting for the whole batch to complete, as and when a single sentence gets completed, they remove that sentence and they attach a new sentence to it. Here, as soon as S1 is completed, they are attaching S6 to it, and as soon as S3 is completed, they are attaching S5 to it. So this way, we can utilize the parallelization nature of the GPUs, and we don't have to like underutilize the GPUs. So that's the nature of it. And another technique which is when it comes to batching, right? It's paged attention. So one other challenge that we have is, let's say when you have a batch of 4 sentences, and when I execute it, I have to allocate pre-allocate a set of memory chunks in my GPU RAM, right? So the usual way of doing it is they pre-allocate like 1000. If the maximum sequence length that you want to generate is 1024 tokens, they usually like pre-allocate like 4 into 1024 continuous strings. So this way we are allocating lot more than what we actually require. In some of the sentences like hi and hi, how are you as a response, we don't need to allocate like 1024 tokens worth of memory into the RAM. So this is taken care by paged attention mechanism, wherein this is probably you would have all read in the operating system concepts, right? Block tables. So wherein instead of allocating a contiguous set of points in memory, they maintain a block table, and then as and when the tokens come in, they refer the block table to allocate the memory in the cache blocks. So this has given like a very good improvement in inference speed. So currently VLLM with combination of paged attention and the continuous batching that we saw before is one of the most efficient libraries to inference LLM. So it is somewhat better than, sometimes even twice as fast as text generation inference, and you can see, right, it is it is a lot faster than the vanilla Hugging Face inference that you do. And the text generation inference, this metrics was calculated when TGA didn't have paged attention and continuous batching. Now they have implemented paged attention and continuous batching as well. So they are like very close, but still VLM is currently has shown to be better. And this is how you can utilize VLLM. So you can install VLLM, it's as simple as that. And then you can create an endpoint with this commands. So that would open, instantiate an API server for your model, and then you can do a curl request or any API request to get the response. And so the next optimization that can be done is speculative sampling. So one challenge, again, with generating tokens one by one is that you can't parallelize it, right? But when you give a set of prompts to a model, the initial prefix that you give as a model, let's say usually, let's say you are an intelligent agent, or you are a so and so, and you have to complete this task, right? This particular prompt is, if it's given as a batch, when given as a batch, can be parallelized easily, because we don't have to calculate the KV cache one by one. It happens at a parallelized scale. So that way, so this prompt is called as prefix, and then the individual tokens that we generate is called as the decoding stage. So the prefix stage is always faster. So this speculative sampling, what it does is it tries to take advantage of this difference. So instead of, let's say if you have a 34 billion model, and instead of that model going and decoding tokens one by one, they use a smaller model, probably a 7 billion model or a 1 billion model. It does the decoding for the bigger model, for the same prefix that is given. It does the decoding for the bigger model, and then whatever that got decoded by the smaller model is fed as prefix to the larger model, and then finally they compare what was generated by a 7 billion or 1 billion model with 34 billion, and whatever that matches the probability distribution, right? They take that into consideration, and so on they generate from there. So this clever way of optimizing generation, it gives us like 1.5 to 2x times better throughput when we do the inference. So this is from the paper, like they sample the tokens from, so Q is the actual bigger model, and P is the smaller model, and then they sample it, and then they compare the distribution. So that is called as rejection sampling. They do rejection sampling to compare the bigger model distribution with the smaller model distribution, and then they finally accept or reject the distribution. So as I said, it's 1.5x to 2x faster. This hasn't been yet included in many of the popular libraries like TGA or VLLM. It's still being been implemented. But if you want to there are things to consider when you want to use speculative sampling, right? You need a draft model, smaller model, which has been trained on the same data as the bigger model. Like for example, you have Llama, right? Llama has been trained, we have 70 billion Llama model and then 7 billion Llama models. So in that case, both the models were trained on same distribution of data. So you need a model that has the same, more or less the same distribution. That is one criteria. The second criteria is the draft model should be of a smaller size so that you get an advantage of a better speed. But at the same time, it should also be good in predicting the next tokens so that the generated, but whatever that got generated by the smaller model is not rejected always. So that would indeed increase the time that it takes, right, rather than decreasing it. So that's the idea of it. And then the overall intuition of this speculative sampling is that when you generate long sentences, there will be a chunk of tokens that is usually easier to predict, right? Like, let's say, again, the same example. When someone says hi, most of the reply would be how are you, right? You don't need a 70 billion model to generate that. So you can use a smaller model like 7 billion model to generate that, and then you just see if it falls in the same distribution as the bigger model, and then you accept it so that that way you are reducing the time taken for inferencing. So if you want to use this, try this today, there is this implementation from this repository. You can try them. It's not currently available, as I said, in popular libraries yet, but there is a variation of it available in transformers, which is, I think it's called as assistive decoding or something. You can also give that a try, or you can also use this library to give the speculative sampling a try. So again, in our internal benchmarks, it gave 1.5x to 2x time improvement. So how are we doing on time? Yeah. The other optimization that we can do, and the most popular one, is quantization, right? So as we saw in the previous slides, the amount of memory required by a model depends on one of the criteria is the number of floating points that you are representing the weights, right? So if it's an int based quantization, for a 7 billion model, you just need 7 GB of space, and so on and so forth, right? So there are different types of quantization that you can do, like GPTQ, AWQ, and so on. LLM intake and so on. I'm not going into details of it, but quantization is one of the approaches where you can optimize a model. There could be a slight decrease or degeneration in your accuracy, but if you are looking for speed in inference, then if it makes sense for you, you can do the trade-off. Quantization, so if you want to do a quantization with vanilla Hugging Face transformers, you can do this. So initially, when you are loading a 16-bit model, right, start code array 7B, it takes memory uses around 15 GB. But when you use it with, when I load it in 8-bit, so you have a parameter for load in 8-bit, it just takes half the memory of it. And if you want to enable the quantization, so in text generation inference library, you can do this flags, quantize bits and bytes, quantize bits and bytes, NF4. So it internally uses bits and bytes to do the intake conversion, and it does the inference. But one catch here is when you do bits and bytes kind of quantization, the inference time would be expected to be longer than an FP16 based inference or equal to it. But one advantage that you would get is the amount of memory that is taken up in a GPU. If you want to have a smaller GPU, you have a smaller GPU, and if you want to fit a bigger model, probably using a quantization, and if you're not worried about the speed trade-off with bits and bytes, then you can use that. And parallelization, like you can, there are various parallelization that can be done, right? Model parallelization, pipeline parallelization, tensor parallelization, and so on. So this is one way to parallelize it using the accelerate library. So here, and there is also, if you are trying to load a bigger model, usually loading it just using a vanilla Hugging Face transformer would take a lot longer, because it copies all the weights into RAM multiple times, and then the weights get initiated. So using device map equal to auto would reduce the load time of it. You can see the difference, like there is like 4 times difference in loading the model. And the other method wherein you can optimize your model is pruning and pruning, right? So this was, pruning as a method was very popular during the BERT era, because most of the BERT or one of the major use cases of BERT was in inferencing on CPUs. When you prune your weights, you will have like sparse matrices, and to do the matrix calculation with the sparse matrices, you would typically require a kernel that suits sparse matrix multiplication. That is little trickier to be implemented in GPU. But it has been already done in different Intel CPUs. So that's when the BERT, since majority of the cases, the BERT can't be inferenced in a CPU-based environment. So we had distillation, we had pruning, right? So pruning was very popular with BERT-based models. But when it came to LLM, since all these models are a billion parameter of scale, and it can't be efficiently inferenced in CPUs, the distillation was not that popular. But there has been a new development with DSparse library. They have introduced a pruning along with the distillation, wherein they do like 2 stages of pruning. One is they train a teacher model without any pruning. Like let's say you are training a bigger 7 billion model on a sentiment classification. They first fine-tune the model on a sentiment classification task, and then they do pruning along with distillation. So they make the weights sparse, and then like they will cut down like 60-70% of the weights, and then they do a knowledge distillation from a teacher model to the student model, and they also do quantization. So that way they are able to like get a reasonable performance on a CPU. You might not yet use it on a production setting, but still, if you want to like try a model on your consumer CPUs, this might be a way. But one catch is that they are not yet supporting many models. They have started with MPT. They have a roadmap to implement Llama and Mistral and so on. But they have started with MPT. And again, the other catch is it requires multiple stages, right? First, you would need a teacher model to be fine-tuned, and then you would need that to distill the student model. So, so you can see the difference, right? We get like 7x the speed up on CPUs, just holding like 60%, making 60% of the weights as sparse. That is only using 40% of the weights. They were able to get like close accuracy to what we can achieve with the full without sparse model. So there is like 7x faster text generation. So the difference that we see with the FP32, and also inferencing it on a CPU-based environment. And this is how, if you want to use this one today, you can use the library. And so they have a pre-trained model for MPT. They have trained it on a Dolly dataset. So if we had to do it, we had to train our own model and use it here. So the other special mention for optimization is NVIDIA's TensorRT LLM. So the NVIDIA has recently brought a variation of TensorRT for TensorRT LLM. This again bakes in all the optimization that we saw till now, and it also includes a few more other optimization as well. From our internal benchmark, TensorRT was able to perform like 20-30% better than VLLM. So VLLM was the best performing inferencing tool prior to that, and TensorRT was able to give like a 20-30% over that. And they also support like int8 and FT8 inference. So that will give you like even more further improvement, like 2x the improvement in scale. So they already support these models out of the box, but one challenge is that it's still new, so there are like certain rough edges, and also it's not as easy as using a VLLM or a TGI yet. So yeah, that's pretty much I wanted to talk today, and so these are some of the sources that I would want to acknowledge, and if you are interested, you can read about further. And yeah, thank you.